This is first module of chapter 8. Chapter 8 deals with ordinary differential equation. We know that the ordinary differential equation or partial differential equation is a very important topic to model several real life problems. For example, Newton's second law of motion is nothing but a second order ordinary differential equation, and we know that using this law we can solve several dynamical problems or particle dynamics problem. A lot of analytic methods are developed to solve ordinary differential equation, but all this method needs in-depth mathematical knowledge. Also, it is not possible to solve third order and higher order ordinary differential equation with the help of analytical methods. So, lot of numerical methods are developed to solve ordinary differential equation. Among them, few methods are discussed in this chapter. In module 1 of chapter 8, we consider Runge-Kutta methods to solve ordinary differential equation. Now we define some basic terminologies which are required in numerical solution of ordinary differential equation. First, we consider the first order differential equation of the form dy dx equal to f of xy with the initial condition x equal to x0 and y equal to y0. So, this is the problem, first order differential equation. If the analytic solution of an ordinary differential equation, in short ODE, is not available, then we will go for numerical solution. If the analytical solution is available for a particular differential equation, then we apply analytical method and not numerical method. The numerical solution of a differential equation can be obtained in one of the following two forms. The first one is the power series solution of for y in terms of x. Then the value of y can be obtained by substituting x equal to x0, x1 up to xn. Note that in power series solution, the interval of convergence is to be measured or the solution is valid if the series is converges within certain interval of convergence. In numerical solution, a set of tabulated values for y for given x equal to x0, x1 up to xn with spacing h. So, these are the basic two methods to get the numerical solution of a differential equation. Now, we consider one particular type of ordinary differential equation called the initial value problem, and that one is defined as the problems in which all the conditions are specified at the initial point only are called the initial value problem, or in short IVP. That means all the conditions are specified at a particular point or at a single point. On the other hand, the ordinary differential equations of order 2 or more and for which the conditions are specified at 2 or more points are called boundary value problems, and this is denoted by BVPs. The method to find approximate solution of an initial value problem are called finite difference method or discrete variable method. In numerical method, the differential equation is converted to discrete algebraic equation. The solution are determined at a set of discrete points called a grid or mesh of the points. That is, a given differential equation is converted to a discrete algebraic equation for the given grid or mesh points. By solving each equation, we get an approximate solution of the given differential equation. This is the main concept of numerical solution of ordinary differential equation as well as partial differential equation. A finite difference method is convergent if the solution of the finite difference equation approaches to a limit as the size of the grid spacing tends to 0. That means, if the spacing h tends to 0, then the solution set of solution converges to a point. But in general, there is no guarantee that this limit corresponds to the exact solution of the differential equation. So, this is very important observation for numerical solution. Mainly two types of numerical methods are developed. The first one is called the explicit method and second one is called implicit method. If the values of yi plus 1 depends only on the value of yi, that means the previous value of y, and h, the step length, and the given function f of xi, yi, then the method is called explicit method. Otherwise, the method is called implicit. In implicit method, the value of yi plus 1 depends on the value of yi plus 1 and the other values of y. Now, we consider the most simplest but crude method, that one is known as Euler's method to solve an ordinary differential equation of the form dy dx equal to f of xy, where the initial condition is y at x0 equal to y0. That means Euler method is applied to solve the equation of the type 3. Let x1 equal to x0 plus h, where h is a small quantity, it may be negative or positive. In general, h is a positive quantity. Then by Taylor series, y1 equal to y at x0 plus h, and by expansion of Taylor series it becomes equation 4, that means y0 plus h into f of x0 comma y0 plus h square by 2 into second derivative of y at c1, where c1 is a constant lies between x0 and x. Then by neglecting second order terms and higher order terms, we get y1 equal to y0 plus h into f of x0 comma y0. So, this is the Euler's equation to find the value of y1 from the given differential equation mentioned in equation 3. In general, yn plus 1 equal to yn plus h into f of xn comma yn, and this relation is true for all n equal to 0, 1, 2 and so on. So, this is the general scheme to solve ordinary differential equation by Euler's method. Note that this is a very simple method to get the solution of any first order differential equation of the form of equation 3. This is a very slow method. To find a reasonable accurate solution, the value of h must be chosen as very small. The Euler's method is less efficient in practical problems because if h is not sufficiently small, then this method gives inaccurate result. So, this is a very crucial or important point to solve any equation, differential equation with the help of Euler's method. Now, the value obtained by Euler's method can be modified, and the new method is known as modified Euler's method. In this method, the value of f at x0 y0 is replaced by the average of f of x0 comma y0 and f of x0 plus h, that means x1 comma y10, where y10 is the 0th approximation or first value of y1, and that one is obtained by Euler's method or Euler formula. That means y10 equal to y0 plus h into f of x0 comma y0. That is, the modified Euler's method is the first approximate value of y1 is denoted by y11, which is equal to y0 plus h by 2 into f of x0 comma y0 plus f of x1 comma y10, where y10 is given by y0 plus h into f of x0 comma y0. This is the Euler's method, and equation 7 is the modified Euler's method. Note that the value of y1 depends on the value of y1 in previous iteration. That means this method is implicit method. That means the modified Euler's method is implicit method, but the Euler's method is an explicit method. Now, we consider another important method, or called the first Runge-Kutta methods, is second order Runge-Kutta method. This is very simple method to get the solution of first order ordinary differential equation. Now, we deduce this method from modified Euler's method. The modified Euler's method is this one, given by equation number 8, y1 equal to y0 plus h by 2 into f of x0 comma y0 plus f of x1 comma y1 0, where y1 is given by Euler's formula. Now we substitute the values of y1 0 to equation 8, we obtain this expression. Note that the last term is replaced by f of x0 plus h comma y0 plus h into f of x0 comma y0. Let k1 equal to h into f of x0 comma y0 and k2 equal to h into f of x0 plus h comma y0 plus h into f of x0 comma y0, and which is equal to h into f of x0 plus h comma y0 plus k1, because k1 is nothing but h into f of x0 comma y0. That means equation 9 represents the value of k2, and the first equation of equation 9 is k1. So using this notation, equation 8, that means the modified Euler's method, becomes y1 equal to y0 plus average of k1 and k2, that means half into k1 plus k2. So this formula is known as second order Runge-Kutta method. Note that this is an explicit formula, whereas the modified Euler's method is an implicit method. So this is very important and interesting observation. The same formula is converted into second order Runge-Kutta method, then the formula is explicit form and the modified Euler's formula remains in implicit form. Note that the local truncation error of this method is order of h cube, where h is the step length in the arguments. This formula, that means second order Runge-Kutta method, can be derived independently, that means without taking the help of modified Euler's method. So for this purpose, we assume that y1 equal to y0 plus a into k1 plus b into k2, where a and b are some constant, where k1 is taken as h into f of x0 y0, similar to the previous one, but k2 is taken as in different form, that means k2 equal to h into f of x0 plus alpha h comma y0 plus beta into k1, where a, b and alpha beta are constant. Now by Taylor series, y1 can be written as y of x0 plus h, which is equal to y0 plus h into y0 prime plus h square by 2 into y0 double prime and so on. Prime represents the derivative, and this is equal to y0 plus h into f of x0 y0, that means y0 prime is replaced by f of x0 y0 because the differential equation is dy dx equal to f of xy. Similarly, the second term is h square by 2 into del f del x at x0 y0 plus f of x0 comma y0 into del f del y at x0 y0 plus the terms of order h cube, that means higher order terms of h square and h cube, h4 and so on. And note that the second term is replaced by the formula df dx equal to del f del x plus f of xy into del f del y. This is available in differential calculus, and this is obtained by chain rule. Now k2 equal to h into f of x0 plus alpha h comma y0 plus beta k1. By Taylor's theorems for two variables, we get h into f of x0 y0 plus alpha h into first derivative of f at x0, partial derivative of f with respect to x at the point x0 y0 plus beta into k1 into first partial derivative of f with respect to y at x0 y0 plus order of h square. And after multiplying all the terms by h, we obtain this expression. Now we substitute all these value to the equation 12, we get this expression. Now to find the values of a, b, alpha and beta, we compare this equation for the coefficient of f, fx, that means del f del x and del f del y, both sides of the above equations, and we get a plus b equal to 1. Note that the coefficient of h into f of x0 y0 is a plus 1 in the right hand side and it is 1 in left hand side, and the second term is alpha b equal to half, and third one is beta b equal to half. So, these are the three equations, and from these three equations we can determine the values of 4 parameters a, b and alpha beta. Obviously, alpha and beta are same. Note that the number of equations is 3 and variable is 4. Therefore, we can choose the value of one arbitrary variables by any arbitrary real numbers. Therefore, the system of equation has many solutions. It is obvious because the number of equation is less than the number of variables. However, usually the parameters are chosen as alpha equal to beta equal to 1, then we get a equal to b equal to half. So, this is one particular choice of alpha beta and ab. For another choice of the parameters we get another second order Runge-Kutta method. So, for this reason this method, that means second order Runge-Kutta method, is called methods. So, for these parameters equation 12 becomes y1 equal to y0 plus half into k1 plus k2 plus order of h cube, that means the truncation error is order of h cube, and k1 equal to h into f of x0 y0 and k2 equal to h into f of x0 plus h comma y0 plus k1. So, this is the famous second order Runge-Kutta method to solve first order differential equation of the form dy dx equal to f of xy. Now, we describe another Runge-Kutta method known as fourth order Runge-Kutta method. The fourth order Runge-Kutta formula is defined as y1 equal to y0 plus 1 by 6 into k1 plus 2 into k2 plus 2 into k3 plus k4. That means the second term is nothing but the average of k1, k2, k3, k4 with weights 1, 2, 2 and 1, where k1 equal to h into f of x0 comma y0, k2 equal to h into f of x0 plus h by 2 comma y0 plus k1 by 2. Note that the value of k1 is used to find the value of k2, k3 is h into f of x0 plus h by 2, the x value is same, but the y value is different, that one is y0 plus k2 by 2, and k4 equal to h into f of x0 plus h comma y0 plus k3. So, these are the values of k1, k2, k3 and k4. So, equation 16 give the value of y1 when k1, k2, k3 and k4 are available. So, using the same technique we can calculate the value of y2 when the value of y1 is available. In general, the I plus 1 value, that means yi plus 1, is given by the formula yi plus 1 by 6 into k1i plus 2 k2i plus 2 k3i plus k4i, where k1i, k2i etc. represents the ith value of k1, k2, k3 and k4 and so on, where k1i equal to h into f of xi yi, k2i equal to h into f of xi plus h by 2, comma yi plus k1i by 2, k3i equal to h into f of xi plus h by 2, comma yi plus k2i by 2, and k4i equal to h into f of xi plus h, comma yi plus k3i, and these relations are valid for I equal to 0, 1, 2 and so on. So, this is the fourth order Runge-Kutta method to solve ordinary differential equation of first order of the form dy dx equal to f of xy. Now, we consider one example to illustrate the second order and fourth order Runge-Kutta method. The differential equation is dy dx equal to x minus y square with the initial condition x equal to 0 and y equal to 1. Our problem is to find the value of y when x equal to 0.2. So, in this case x0 equal to 0 and y0 equal to 1, this is the initial value of x and y, and f of xy equal to x minus y square, this is the value of the function f of xy. Now, we consider second order Runge-Kutta method to solve this equation. for this method we consider h equal to 0.1, then k1 equal to h into f of x0 comma y0, which is equal to minus 0.1, k2 equal to h into f of x0 plus h comma y0 plus k1. After simplification it is equal to minus 0.07100. Therefore, y1 equal to y at 0.1, that means the value of y1 is nothing but the value of y when x equal to 0.1, which is equal to y at 0 plus half into k1 plus k2. So, after simplification, after substituting the values of y0, k1 and k2, we get y1 equal to 0.91450. So, this is the value of y when x equal to 0.1. Now, we calculate the value of y2, that means the value of y when x equal to 0.2. In this case, x1 equal to 0.1 and y1 equal to 0.91450. So, for this value, k1 is equal to minus 0.073633, k2 equal to minus 0.05071. So, these are the values of k1 and k2. Therefore, the values of y2 equal to y at 0.1, that means y1 plus half into k1 plus k2. So, after simplification, the value of y2 is equal to 0.85233. So, this is the final value of y at x equal to 0.2, and the value is 0.85233. Now, we apply fourth order Runge-Kutta method to find the values of y at 0.2 and y at 0.1. In this case also, h equal to 0.1, x0 equal to 0, y0 equal to 1 and f of xy equal to x minus y square. But k1 equal to h into f of x0 y0, which is equal to minus 0.1, k2 is equal to minus 0.08525, k3 is equal to minus 0.08666 and k4 equal to minus 0.07342. Therefore, y1 equal to y0 plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4, which is equal to this expression, and after simplification it becomes 0.91379. So, this is the value of y when x equal to 0.1. Now, to find the value of y2, that means value of y at x equal to 0.2, h is 0.1, x1 equal to 0.1 and y1 equal to 0.91379. So, using these values, we calculate the value of k1, which is equal to minus 0.07350, k2 is minus 0.06192, k3 is minus 0.06294 and finally k4 equal to minus 0.05239. So, using this value, the value of y2 equal to y0 plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4, which is equal to this expression, and after simplification we get y2 equal to 0.85119. So, this is the value of y2, that means the value of y when x equal to 0.2. The error in Runge-Kutta, fourth order Runge-Kutta method is calculated in this slide. The fourth order method can be written as y1 equal to y0 plus h by 2 by 3 into k1 plus 4 into k2 plus k3 by 2 plus k4. So, note that this expression is similar to the Simpson 1/3 formula for integration with step size h by 2. So, using the same concept, that means the error in Simpson 1/3 formula, we get the local truncation error of this method, that means fourth order Runge-Kutta method is minus h to the power 5 by 2880 into fourth derivative of y at c1, where c1 is a value lies between x0 and x1. That means the order of error of this method is h to the power 5. After n step, the accumulated error is of order h to the power 4. The second order and fourth order Runge-Kutta methods are described to solve a first order ordinary differential equation of the form dy dx equal to f of xy with the condition y at x0 equal to y0. This method can also be extended to solve a pair of first order differential equation, and it can also be applied to solve a system of n first order differential equation. And it is very interesting thing is that this method can also be used to solve second order initial value problems. Now we consider a pair of first order differential equation using Runge-Kutta method. Now we describe Runge-Kutta method for a pair of first order ordinary differential equations. Let us consider a pair of first order differential equations dy dx equal to f of x comma y comma z, and second equation is dz dx equal to g of x comma y comma z with the initial conditions x equal to x0, y equal to y0, z equal to z0. So, this is a pair of ordinary differential equation, and that one is in equation 18, and equation 19 gives the initial conditions. The fourth order Runge-Kutta method to find the values of yi and zi for x equal to xi for a pair of equations is yi plus 1 equal to yi plus 1 by 6 into k1i plus 2k2i plus 2k3i plus k4i. So, this formula is similar to Runge-Kutta method obtained in the previous problems or single first order ordinary differential equation, and second formula is used to find the value of zi plus 1, and that one is equal to zi plus 1 by 6 into L1i plus 2 into L2i plus 2 into L3i plus L4i. Note that the formula for yi plus 1 and zi plus 1 are exactly similar, the form are similar, but the values of the parameters, that means k1, k2, k3, k4, L1, L2, L3, L4 are different. Now, the values of k1i is equal to h into f of xi comma yi comma zi, that means this is similar to the k1 for simple Runge-Kutta method, but only one argument is added, that one is zi with the function f, and similarly the value L1i is equal to h into g of xi, yi, zi. Note that these two expressions are same except the name of the function f and g. k2i equal to h into f of xi plus h by 2, comma yi plus k1i by 2, comma zi plus L1i by 2. And the formula for L2 is exactly similar to the previous one, that means k2i, only the function f is replaced by g. Similarly, the formula for k3 is this one, L3 is this one, both are the similar formula. Here also the function f is replaced by g, and this is the formula for k4i, and this is the formula for L4i. Note that the value of k1 and L1 are used to calculate the value of k2 and L2. So, we have to calculate first the value of k1 and L1, then we shall calculate, or we can calculate the value of k2 and L2. Similarly, for k3 L3 and k4 L4. So, the values of k and L are calculated according to the formula given in equation 21. Now, we consider a pair of first order differential equations dy dx equal to z and dz dx equal to y plus xz. This is the pair of first order differential equation with initial condition y at 0 equal to 1 and z at 0 equal to 0. That means the value of x equal to 0, y equal to 1 and z equal to 0. Our problem is to find the value of y and z at x equal to 0.2. For this problem, we consider h equal to 0.2, and now we have to calculate the values of k1 to k4 and L1 to L4 according to this formula. And for this problem, f of x comma y comma z equal to z and g of x comma y comma z equal to y plus xz. Now k1 equal to h into f of x0 comma y0 comma z0, which is equal to 0, L1 equal to 0.2, k2 is equal to 0.02, L2 equal to 0.2020, and k3 equal to 0.02020. Similarly, L3 equal to 0.20402, k4 equal to 0.04080, and lastly L4 equal to 0.21220. So, these are the values of 4 k's and 4 l's. Now, using this value, we have y at 0.2 equal to y1, which is equal to y at 0 plus 1 by 6 into k1 plus 2 into k2 plus k3 plus k4. So, using the values of k1 to k4 and the values of y0, we get this expression, and after simplification it is equal to 1.0202. So, this is the value of y at x equal to 0.2, and similarly z at 0.2, which is equal to z1 equal to z at 0 plus 1 by 6 into L1 plus 2 into L2 plus L3 plus L4, and after substituting the values of L1, L2, L3, L4 and the value of Z0, the expression is this expression. After simplification it is equal to 0.20404. That means the value of y and z are respectively 1.0202 and 0.20404 when x equal to 0.2. So, this is the solution of the given ordinary differential equation with the help of fourth order Runge-Kutta method. Now, the Runge-Kutta method can be extended to solve a system of first order differential equation. Let us consider the following system of first order differential equation. The first one is dy1 dx equal to f of f1 of x comma y1 comma y2 up to yn. Here x is the independent variable and y1 to yn are the dependent variables. The second equation is dy2 dx equal to f2 of x comma y1 comma y2 up to yn, and the nth equation is dyn dx equal to fn of the same variables. So, this is a system of n equation, n first order differential equation, and the initial conditions are x equal to x0, y1 equal to y10, y2 equal to y20, and lastly yn at x0 equal to yn0. So, this is the initial condition to solve the above equations. In this problem, x is the only independent variables and y1 to yn are the n dependent variables. So, our problem is to find the value of y1, y2 up to yn for given values of x. The given system of equation can also be written in a vector notation as follows: dy dx, where y is a vector containing the variables y1 to yn, and this is equal to f. F is also a vector containing the functions f1 to fn, and it is function of x, y1, y2 up to yn with the initial condition y at x0 equal to y0. Note that both y and y0 are the vectors. Then the fourth order Runge-Kutta method for this problem is yj plus 1 equal to yj plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4, where all the quantities, that means k1, k2, k3, k4 and yj and yj plus 1 are the vectors. What the value of the parameters k1, k2, k3, k4 are given by equation 26, and all the ki1, ki2, ki3 and ki4 are calculated with the help of equation 27. Hereykj is the value of the variable yk evaluated at the point x equal to xj. So, equation 27 gives the values of ki1, ki2, ki3 and ki4. Equation 26 gives the values of k1, k2, k3 and k4, and finally we can calculate the value of y j plus 1 using the formula given in equation 25. Now we consider second order initial value problem, and this problem can be solved with the help of Runge-Kutta methods, either second order Runge-Kutta method or by fourth order Runge-Kutta method. Let us consider the following second order initial value problem. The equation is ax into second derivative of y plus bx into first derivative of y plus cx into y equal to fx, where ax, bx, cx and fy are the functions of x only, and the initial conditions are x equal to x0, y equal to y0 and dy dx at x0 equal to z0. This problem can be converted to two first order equations. For this purpose, let first derivative of y at x is taken as zx, that means dy dx equal to zx, then d2y dx2 is equal to dz dx, and using this notation the equation 23, that means the given initial value problem, reduces to dy dz equal to dy dx equal to z, and the second equation becomes dz dx equal to g of x y z with the initial conditions x equal to x0, y equal to y0 and z equal to z0. This is a pair of first order differential equations, and this equation can be solved with the help of second order or fourth order Runge-Kutta methods described in previous sections. The value of y is the solution of the given initial value problem, and the value of z is the first order derivatives. That means the value of z is the derivative of y evaluated for a given x. This is the extra value obtained by the process, that means obtained by the Runge-Kutta method. Now we consider the following second order initial value problem: d2y dx2 minus 2 dy dx plus y equal to x plus 1 with the initial condition x equal to 0, y equal to 1 and dy dx equal to 0. Our problem is to find the value of y at x equal to 0.1 using fourth order Runge-Kutta method. So for this purpose we assume that dy dx equal to z, then the given equation reduces to dz dx minus 2z plus y equal to x plus 1, or it can be written as dz dx equal to 2z minus y plus x plus 1, and let it be g of x comma y comma z. Therefore, we have a pair of first order differential equation. The first one is dy dx equal to z, and second one is dz dx equal to 2z minus y plus x plus 1. And for this problem the initial conditions are x0 equal to 0, y0 equal to 1, z0 equal to 0 and h equal to 0.1. So we calculate the value of k1, L1, k2, L2, k3, L3, k4 and L4. So with this value we have y at 0.1 equal to y0 plus 1 by 6 into k1 plus 2 into k2 plus k3 plus k4, and after simplification the value of y at 0.1 equal to 1.000175, and the value of z at 0.1, and which is nothing but first derivative of y at 0.1, and it is equal to 0 z0 plus 1 by 6 into L1 plus 2 into L2 plus L3 plus L4, and it is equal to 0.005346. Therefore, the required value of y at x equal to 0.1 is 1.000175, correct up to 6 decimal places. In addition, we get the value of first derivative of y at x equal to 0.1, and it is equal to 0.005346. Now we consider another modification of Runge-Kutta method, this one known as Runge-Kutta Feldberg method, Many variants of Runge-Kutta methods are available in literature. The Runge-Kutta-Feldberg method gives better result by solving the differential equation twice using step sizes h and h by 2. In this method, at each step, two different approximations for the solution are calculated. If the two approximations are closed, then we obtain the final solution of the given differential equation. If the approximation does not meet the required accuracy, then the step size may be reduced. So, in each step the following 6 values are required, that means k1 equal to h into f of xi yi, k2 equal to h into f of xi plus h by 4, comma yi plus k1 by 4. This is similar to the value of k2 for the Runge-Kutta method. K3 is different, the expression is this one. Note that the value of k3 depends on the value of k1 and k2. And this is the expression for k4, this value depends on the value of k1, k2 and k3. This is expression for k5 and this one expression for k6. Note that the values of k1, k2, k3, k4, k5 and k6 depends on the values of the previous case. Now, using these values, we can calculate the value of yi plus 1 using the fourth order Runge-Kutta method. That means yi plus 1 is equal to yi plus 25 by 216 into k1 plus 1408 by 2565 into k3 plus 2197 by 4104 into k4 minus 1 by 5 k5. So, this is the fourth order Runge-Kutta method. Note that only 4 k's are used in this formula, that is why this formula is known as fourth order Runge-Kutta method. In this formula the value of k2 is not used, that one missing. Another value of y is determined by the following fifth order Runge-Kutta method, that one is this one. That means the fifth order Runge-Kutta method is given by equation 34 and the value of yi plus 1 is denoted by yi plus 1 star. The equation 34 is the fifth order formula because it contains 5 k's, k1, k3, k4, k5 and k6. If these two values are closed, that is, if the difference of the absolute value of yi plus 1 and yi plus 1 star is small enough, then the method gives the solution of the given problem. Otherwise, the computation is repeated by reducing the step size h. This method gives more better result than the conventional fourth order Runge-Kutta method. So, this method is known as Runge-Kutta-Feldberg method. In this module, the second order and fourth order Runge-Kutta method, these are the basis Runge-Kutta methods are described, and we have shown that the Runge-Kutta methods can be used to solve a pair of first order ordinary differential equation. It can be used to solve a system of first order ordinary differential equation. It can be used to solve second order initial value problem. Also, this method can be used to solve third order and higher order initial value problems. But note that this method needs lot of evaluation of functions. This is the drawback of this method, but this method gives a better result compared to the other methods like Euler's method, modified Euler's method, Taylor series method, Picard's method. These are available to solve the ordinary differential equations. In next module, we consider another type of methods known as predictor corrected methods.